Okay, so we got 59 heads in 100 flips of David's coin. How unlikely is that? What are some ways that we could try to calculate a p-value? Well, now, if we're flipping a presumably fair coin 100 times, remember, we're assuming for now that the null hypothesis is true. That's how we base our calculations. If we flip a fair coin 100 times and we count the number of heads, x, then x will have a binomial distribution with n equals 100 trials and p equals 1/2, the probability of heads on a flip of a fair coin. So if in fact we have a fair coin, then before we flip the coin, we know that x, the number of heads, will have this distribution. And Excel can crank out these probabilities. These are very tiny, right? The probability you get no heads or exactly one head, very, very tiny. For example, this here is about 8 times 10 to the negative 31st. But here's the thing. We're asking about 59 heads. We actually got 59 heads out of 100 flips. So a student might ask, well, what's P of 59? What's the probability of getting exactly 59 heads? Okay, well, if we scroll down, we see that the probability of getting exactly 59 heads is about 1.6%. And you might go, well, gosh, that sounds very, very low. But I might argue with you, in fact, I will argue with you, that this analysis isn't really fair. Because think about it. If you flip a presumably fair coin 100 times, what is the most likely number of heads? What value for x? What number of heads here is most likely with the highest probability? It's going to be 50 heads. X equals 50 heads. But look here, even the probability of getting exactly 50 heads is not that high. It's not even 8%. It's just a bit below 8%. So I would argue with you that just using as a p-value the probability of getting exactly the number of heads you got, that's not really fair. That's not really appropriate. Because even P of 50, the most likely number of heads for a fair coin, is not that high. So that's why we consider tail probabilities. All right. It's not enough to look at P of 59. 50 is the most likely number of heads, and even P of 50 is not that high. It's not even 8%. So the fact that P of 59 is only about 1.59% or 1.6%, that doesn't tell me that much. Instead, I should look at a tail probability. When I say tail probability, please don't confuse that with the fact that a coin can come up heads or tails. I'm using the word tails in different senses here. All right. It is more appropriate to find the probability of getting at least 59 heads if a fair coin is flipped 100 times. That will at least get us a one-tailed p-value. So instead of just P of 59, I'm going to consider the probability that x is at least 59 heads. So I'm going to add together P of 59 plus P of 60, the probability of getting exactly 60 heads, plus P of 61, the probability of getting exactly 61 heads. These are disjoint events here, so I can add up the probabilities. In any situation, you only have one number of heads, and so on and so forth. And then finally, P of 100. You add up all these probabilities, and I claim that you'll get about 4.43%, 0.0443. In fact, I had Excel do that. I had Excel take these probabilities from P of 59. You get very close to 0 here anyway, right? But I had Excel add up all these probabilities from P of 59 to P of 100. Not that these really mattered way down here. But when you add up all those probabilities, bingo, we get about 4.43%. About 4.43% if you add up all the probabilities from P of 59 through P of 100. So this one-tailed probability, the probability of getting at least 59 heads, is about 4.43%. So that is one possible p-value you could use, but again, someone could object. Someone could say, just like with the red card, black card example, why not consider a two-tailed p-value? And different people would use different measures. By symmetry, we can add on the probability of getting at least 59 tails. Now, if you get at least 59 tails, if you want to use our Excel spreadsheet, it helps to know that at least 59 tails means at most 41 heads. We're assuming, again, for now, the coin is fair. We're assuming symmetry for now. That's why a two-tailed analysis might be appropriate. So if we do that, well, the probability of getting at least 59 heads is about 0.0443, or about 4.43%. Well, likewise, the probability of getting at most 41 tails is exactly the same, about 0.0443, or about 4.43%. That's when you add up everything from P of 41, P of 40, P of 39, all the way down through P of 0. Although, again, we get very, very, very close to 0 down here, right? All right. So this is the same probability as before. These two-tailed probabilities are the same. So the probability of getting at least 59 heads or at least 59 tails, that is at most 41 heads, okay? That's twice the 0.0443 we got earlier for one tail. It's about 0.0886, or 8.86%. So that's another way that you can get a p-value. This is the two-tailed p-value based on our result of 59 tails. Or I'm sorry, 59 heads. 59 heads. But this two-tailed p-value considers the probability of getting at least 59 heads or at least 59 tails. You could have used a normal approximation, maybe with continuity corrections, and you could have found this on your own without using Excel in such a way. Here I was being very detailed. I was very precise here, but you could have used a normal approximation, especially with continuity corrections. That's nice. So what do we decide to do about the null hypothesis? Literally, what's our decision? Do we reject the null or do we not reject the null? Well, it depends on which p-value we take. Do we take the one-tailed or two-tailed p-value? Bear in mind that decision should be made before you even flip the coin. The decision basically as to whether this is a one-tailed test or a two-tailed test, that should be part of the design of this whole experiment before you even get your sample. Okay, but whichever p-value we have, whether it's one-tailed or two-tailed, and also how low is too low? In particular, what's alpha? Too low means you're less than alpha. The p-value is less than alpha. We'll talk more about that later. When we conclude, well, our conclusion will depend on our decision. And looky here. And this is why some journals and some articles in journals give p-values even more so than alpha, because different organizations might have different standard values for alpha. 5% is usually standard, but it's not universal. 5% is usually considered standard, but here's the thing. If alpha is 5%, 0.05 or 5%, if 5% or 0.05 is our threshold for what it means to be unusual, remember, if the p-value is low, let's say lower than alpha, then the null must go away. Well, if your threshold is 5%, then this one-tailed p-value is too low. But this two-tailed p-value is not too low. It's higher than alpha, so it wouldn't be too low. So if you take this one-tailed p-value, if you're doing a one-tailed test, you would reject the null hypothesis. The assumption of a fair coin would be rejected. If you take this two-tailed p-value, about 9%, well, for this value of alpha, you would not reject the null. And the idea of a fair coin is still viable. Alpha, this threshold for what it means to be unusual. If the p-value is low, the null must go. Lower than what? Alpha. We'll talk about that next time. Remember, a p-value is a probability of obtaining sample results at least as extreme, that's a tail idea, as what we observe, assuming that the null is true. This implies tail. It could be one-tailed or two-tailed, right? We're going to use either one-tailed or two-tailed analyses for a z-distribution, a t, or a chi-square, but we're going to deal with one or two tails. A p-value is a probability of obtaining sample values at least as extreme as what we observe, assuming the null is true. That's the definition of a p-value. Alpha, we're going to talk about next time, the significance level.